Quite often during our discussions throughout this course, we're going to be talking about graphing, and you may recall that graphing is accomplished on a plane that is called a rectangular coordinate system, or perhaps the Cartesian plane. It's called the Cartesian plane in honor of the great French mathematician René Descartes. You may also recall that the Cartesian plane is composed of two intersecting number lines, a horizontal number line called the x-axis and a vertical number line called the y-axis. The two number lines intersect at 0 on both number lines. And along the x-axis, positive values lie to the right, negative values to the left. On the y-axis, the positive values lie above and the negative values below the intersection point. The intersection point is called the origin of the coordinate plane. Now, positions on this coordinate plane are identified using two numbers. Those two numbers are said to be ordered, and an ordered pair might look like this. The position 4, -2. It's called an ordered pair because the first item represents a horizontal distance, the second item a vertical distance, hence the order idea. These are called the coordinates of a certain point, and this is the x-coordinate and that the y-coordinate. Now, to locate a point, we begin at the origin and we move according to the distances indicated. 4 horizontally means from the origin go a distance of 1, 2, 3, 4, and then -2 means down 2 vertically, so we go down 2, and here then is the point for -2. Let's locate a couple of other points. How about the point -5, -3? From here, -5, that means to the left, is the negative direction horizontally, so it's -1, 2, 3, 4, 5, and then down 1, 2, 3. So here's the point -5, -3. Now I am plotting points or graphing according to the coordinates that we are talking about here. Suppose we are talking about the coordinates 0, 4. Well, let's see. 0, 4. That means the first component, the horizontal component, is 0. That means we don't go any distance this way. And then 4 means we go up 4 to arrive at the point 0, 4. And one more, the point -2, 0. -2 means to the left 2. You see the horizontal distance, -2 means to the left 2. And then 0 means no distance up and down. This is the point -2, 0. Okay, so we're graphing now. Now, if we have a place on the coordinate plane like, let's say this place, and we want to discover its coordinates, then we would count from the origin a horizontal and vertical distance to that point. So from the origin, 1, 2, 3, 4, 5, 6, 7 horizontally, and then 1, 2 vertically. So this is the point 7, 2. These are then the coordinates of that point. One thing we can do with our coordinate plane is we can actually develop a formula for calculating the distance between any two points. And this formula then would be called the distance formula. I can just give it to you here, but you might remember it a little better if we show how this formula is developed. I won't take a great deal of time with this, but here's the gist of the idea. Suppose we're talking about the point 2, 3 and the point 10, 9. All right, so these are the coordinates of those 2 points, and we want the distance between the 2 points. The idea is this. I'd like to calculate this distance, and the way that the distance formula is developed, it actually comes from the Pythagorean relationship, which is a relationship between the sides of right triangles. And if we drop a vertical segment down here and then a horizontal segment across to that one, then we have a right triangle formed. And in this right triangle configuration, if we call this side A and this side B and this side C, then we know that by the Pythagorean relationship, c squared is equal to a squared plus b squared. So we have c squared is a squared plus b squared. Now we're going to develop a distance formula, this distance along between the 2 points. So this distance c is what we're after here. So I want to solve this for c. Taking the square root on both sides, I find c to be the square root of a squared plus b squared. Now let's talk about the distances a and b. Now this distance a is a horizontal distance. The coordinates of this point, 10, 3. Now, horizontal distance, distance along a number line, you may recall from before, is calculated as the absolute value of the difference in values, the real number values along the horizontal number line. Now here, we're talking about horizontal distances, so the components for horizontal distance are the 2 and the 10. So this distance A is the absolute value of 2 minus 10, or 10 minus 2, whichever. But at any rate, that A distance is this 2 minus 10, and it's being squared here. In a similar way, the distance from this point to this point, these are vertical distances now, so the second component comes into play here in these coordinates. So it's the absolute value of 3 minus 9 for that distance. So the absolute value of 3 minus 9, or 9 minus 3 if you'd like, and that value is squared. Now, absolute value was put into this distance idea when we were talking about distance on the number line because we wanted to make sure that the value was always positive. Well, it doesn't really matter in this context whether the value is positive or negative because we're squaring. And whether we square a positive number or a negative number, we get a positive result. So the absolute value symbols are unnecessary here, so let's take them off. We come to this situation. Now I'm calling this the distance formula, so we'll label the C value D. We'll just change the labeling on it, D for distance, you see, between any 2 points. So this is the general idea. Now here's what I want you to notice. You see the 2 and the 10 here, the 3 and the 9 here? Now those are actually, those came from this configuration of the right triangle. But the 2 here and the 10 here, gee, I used this 10 and that 2, but I didn't need to use this 10, I could use that 10. You see, I can just use the horizontal components of the 2 given points. And in a similar way, I use the 3 here and the 9. Well, instead of using this 3, I could have used that one. See, I have 2 vertical components here given in those 2 original points. So I don't really need this, the coordinates of this point in order to use this distance idea. I can just use the 2 points given. Now, to generalize the situation, whether I was using the points 2, 3, 10, 9, or simply x, y, or x1, y1, x2, y2. You see, I could use general points to make this kind of development or to develop this distance formula. And the distance formula then emerges like this. This is just a difference in x components, or a distance in horizontal distances, and this is just a difference in y components, or a difference in vertical distances. Now the subscripted numbers here, the subscript numbers, just indicate that these are different x components. And these just say that these are different y components, and that's all. And because this is a 2 and that's a 2, this xy pair, they're related to one another. And the ones indicate that those rascals are related to one another as well. But that's really all there is to it. Now, to make the calculation, we would presumably go from the distance formula, plug the information into a step that looks like this, and perform the indicated operations to find that distance to be, I think in this case, it turns out to be 10. Well, one way that the distance formula can be used is to determine whether or not we have a right triangle if we're given the coordinates of several points. That is, given that we have the points 2, 1, 4, 0, and 5, 7, are these the vertices of a right triangle? Gee, if they are the vertices of a right triangle, then this relationship between the sides exists. You see, the Pythagorean theorem works both ways. That is, the way we generally think about the Pythagorean theorem is that if we have a right triangle, then we have a certain relationship between the sides. C squared equals A squared plus B squared. Okay. It's also the case, though, the other way around, that if we have any ordinary everyday household triangle and we have a special relationship between the sides, namely A squared plus B squared equals C squared, if we have that relationship, then we can determine that we have a right triangle. So it works both ways. Now, in order to determine whether or not we have a right triangle, what we need to do is calculate the distances between these points, you see, and then determine whether or not we have that special relationship between those distances. And those distances represent the sides of some triangle. It might be a right triangle, and we'll find out. Now, we'll use the distance formula 3 times. We want the distance between that point and this one, the distance between this point and that one, the distance between this point and that one. And then we'll check out to see if we have this special relationship. I want to make sure that we understand what we're doing. Let me just sketch what's going on here. We've got the point 2, 1, about right here. The point 4, 0, that's about right here. I didn't think about this a great deal before I started this. Now, all right, here's 4, 0. And then the point 5, 7. Here's 5, and then up 7, 0, somewhere up in this neighborhood, let's say. Now, are these points the vertices of a right triangle? It almost looks like that may be a right angle. I sketched it roughly, so it might be. You know, we just don't know. But that's the idea, that we want distance between the points in order to determine whether or not we have this special relationship between the sides of a right triangle. So we come out to the side, and we say, we're using that formula, and we say, I want the distance between, let's see, 2, 1 and 4, 0. So it's that distance then is the square root of, now I'm using that formula. Generally I say write the formula down, replace within the formula in the first step, and then make your calculations. Well, I'm replacing within the formula right here because I have it written down over there. Difference in x components would be 2 minus 4. It's squared, and I'm adding the difference in y components. That's 1 minus 0 squared. Now let's see, what do I have? I've got d equals the square root of, now let me simplify in my head a little bit. This is negative 2 squared is 4, so that's 4. This is 1 squared is 1, 4 and 1, 5. This is the square root of 5. Okay, good. Now, for another one, for the distance between, let's say 2, 1 and that other point 5, 7, I go distance is square root of difference in x components. I've got 2 minus 5 squared plus difference in y's, that's 1 minus 7 squared. And then that distance is, this is negative 3 squared, that's 9. Negative 6 squared, that's 36. 36 and 9, that's 45. So the square root of 45. Okay, I have one more. I'm just backtracking over here. So I want the distance between the 4, 0 and 5, 7. So I have the square root of, let's see, difference in x components, that's 4 minus 5 squared plus 0 minus 7 squared. That's square root of, this is negative 1 squared, that's 1. This is negative 7 squared, that's 49. So this then would be the square root of 50. Now my three distances are, let's see, I might name these a little bit differently. I have them all labeled as D. That's kind of inappropriate because they're not all the same. So I might call this D1 and D2 and D3. So I've got, let me summarize here. D1 was square root of 5, D2 is the square root of 45, and D3 is the square root of 50. Now, is it the case that c squared is a squared plus b squared? Well, gee, what's a and b? Well, a and b are the legs of a supposed right triangle, and c is the hypotenuse. C is the longest side. What would be the longest one of these? Oh, it would be this. So is it the case that the square root of 50 squared equals the sum of the squares of the other two sides? That's the square root of 5 squared plus the square root of 45 squared. So this would be 50 equals 5 plus 45. Oh, sure, 50 is indeed equal to 50, and therefore we do have a right triangle. If we know the coordinates of 2 points on the coordinate plane, we know that we can use the distance formula to calculate the distance between the 2 points. Well, there's also a formula for finding the midpoint between those 2 points, and it's rather intuitive. That is the method of of calculation is rather intuitive. It works like this. Suppose we have a couple of points on the coordinate plane. We'd like to find the coordinates of the point that's right in the middle between those two. The midpoint formula conceptually works like this. It's just the average horizontal distance. You see the average of the horizontal distances associated with the coordinates of those points and the average vertical distance for the y component of that midpoint. So it's average horizontal distance, average vertical distance. And averages, you know, are calculated by taking some number of things and adding them and then divide by the number of items that you have added. Now here we're just averaging a couple of horizontal distances and a couple of vertical distances. So we're adding two x values and we're dividing by 2 to get the average. And then you add a couple of y values and divide by 2 to get the average. And that's really all there is to it. So it's add the x components, divide by 2, add the y components, divide by 2, and these are the coordinates then of the midpoint. For the points that we have here, the x components are -3 and 7. Collecting those and dividing by 2, we get 2 for the x coordinate of the midpoint. The y components are 1 and 5. Adding those and dividing by 2, we get 3 for the y coordinate of the midpoint. The midpoint then has coordinates 2, 3. Let's see, 2 and up 3. Aha! Here's the midpoint of this segment.
Problems involving formulas. It seems like that if the formula is given to us, or if a formula exists, we don't have to go through this idea of some kind of verbal model in order to find the mathematical model. That we don't need to do that. Well, that's true. But the difficulty with formulas is to recall them. Now, I don't suggest that you try to memorize a lot of formulas, but I do suggest that you try to conceptualize formulas, put them into certain groups, and a lot of times if you do that, if you think of them conceptually, you can come up with a formula on your own. Now, I'm going to show you a method of doing that in just a moment, but here are some familiar figures. We have a square, a rectangle, triangle, and a circle. And for perimeter, that's the distance around the outer edge, we could invent many of these formulas on our own. I mean, after all, if one of the sides of a square is s, then they're all s, and all we're doing is adding s 4 times. So no wonder the formula is 4s. And for a rectangle, we have a length here, a length up here, a width here, and a width up here. So we're adding LW, LW. You see, no wonder it's 2L plus 2W. So we could really come up with these formulas on our own. And it's really just kind of a no-brainer for the triangle. It's A plus B plus C. Just add the 3 sides for the perimeter. Now for the circle, it's rather interesting. It's pi times diameter. It's actually the case that the circumference of the circle, which is its perimeter, is related to the length of the diameter. And as a matter of fact, if you took that diameter and if I could pull it away from the board and then shake it a little bit and make it flexible and lay it along that circumference, you see, along the circle, on top of the circle, it would lay on top of the circle a little more than 3 times. And actually it would lay on top of the circle exactly pi number of times. So the circumference is pi number of diameters, pi times the diameter. All right, let's get into the area idea. And here's where the concept notion comes into play. It's the idea that when you calculate area, you are really just multiplying 2 dimensions, or calculations along 2 dimensions. You're multiplying a horizontal distance times a vertical distance, and that's roughly all you're doing on all of these in all of these formulas. Here, if we're thinking about the area of a square, it's s squared because you're multiplying s times s. And just think about horizontal vertical distance here. All right, so in the area of a rectangle, you're multiplying length times width, sort of a horizontal and vertical dimension idea. Now with the triangle, it's a very similar notion, and we can use the same concept. 1/2 BH. Well, here's how you think about that. Think about, let me erase some of this, and I'll show you what I mean. You see, it turns out that the triangle can be thought of as emerging from or being cut from a parallelogram. And a parallelogram is this. And the formula for the area of a parallelogram is base times height. Now, base times height is just a horizontal distance times a vertical distance. Same concept, you see. And now the triangle is just 1/2 of that base times height. So 1/2 base times height for that formula. For the circle, it's a little bit of a reach to think about horizontal and vertical distances, but not too awfully much. Look at what happens if I kind of make a little diagram like this. Yeah, I'm going to try to do it quickly here, but suppose I subdivide this circle like this. And think about a little square right here and a little square right here and down here and down here. Does it make sense that the area of the circle is somewhat less than 4 times the area of these squares? Now, all this is an r distance for the radius, and this is a radius as well. So the area of that square is r squared, and this is r squared, and that's r squared, and that's r squared. So all of this outer box thing is 4r squared. So the circle's area is somewhat less than 4r squared. Well, it's actually exactly pi r squared. You see, a little over 3 of those r squares is what the area is. And maybe telling this story and illustrating it like this, it would help you to remember that idea. Now, with volume, the notion of concept is that think about area of the base times the height. Now, you can generate formulas for the volume of many different figures. As long as the figure has a flat bottom and it has vertical sides, the concept for volume is area of the base times the height. And that's all. And that idea follows from with the figures that I have here. I've got a rectangular solid. Now think about the base. The base is nothing but a rectangle. And the area of that base is length times width, and then multiply times the height. So area of the base times the height. Here we have a cylinder. The base of it is circular. The area of the base, the area of that circular base is pi r squared. And we multiply times the height to give us the volume of the entire figure. So area of the base times the height is our concept. Now, here's a sphere, and the formula for the volume of a sphere is 4/3 pi r cubed. Doesn't seem to have anything to do with area of base and height and all that kind of stuff. But, you know, maybe if I tell you the story about how this formula came to be, you might tend to remember it a little bit better. And I'll try to give you the short version of this story. But it goes all the way back to Archimedes, the great Greek mathematician. Archimedes is reputed to be one of the 3 greatest mathematicians ever to have lived. And his story is wonderful. He was put in charge of the defense of the city where he lived. He was on a little island off of Greece, actually, and it's called Cyprus now, and it was called Syracuse is what it was called at that time. And the Romans were coming to conquer that area, and he was put in charge of the defenses, and it took them 2 years to conquer this little bitty island off of Greece, and the Romans thought it would take them 2 weeks, but it was all due to the defenses set up by Archimedes. Anyway, it's worth reading if you get a chance to do that. Okay, Archimedes and the rest of the Greeks were concerned with developing formulas for figures such as these, for the geometric figures. And he pondered for a long time about the formula for the volume of a sphere. Here's what he did to come up with a formula. He built a cylinder that was consistent with the idea of a sphere. That is, the cylinder had a base which was 2 times the radius. You see, the diameter was the same as the diameter of the sphere. That is, 2 times the radius was the same as 2 times the radius for the sphere. Okay, and the height of it was the same dimension. That is, the cylinder was as tall as the sphere was as tall. And so that he could actually put the sphere inside the cylinder. And he filled the cylinder with water. And then he carefully put sphere inside the cylinder and allowed the water to be displaced. So here's what he was doing. He took his cylinder and he dropped the sphere into it, and water came out the top. And then he very carefully pulled the sphere out, and the water then settled back into the container. And he measured how much water was in here, and every time he performed the experiment, he found that 1/3 of the water remained in the cylinder. So he reasoned that the sphere had displaced 2/3 of the water in the container, and therefore the volume of the sphere must be 2/3 the volume of the cylinder. So he mathematically performed this calculation. He said, gee, the volume of the sphere is 2/3 the volume of the cylinder, but the volume of the cylinder is pi r squared h. Okay, that's the volume of the cylinder. Now, the trick here is that the height of the cylinder is nothing more than, now notice, the height of the cylinder is nothing more than the radius of our sphere twice. So this h is simply 2r. And so let's see, let's distribute and multiply. We have 2 times the 2/3 here, that's 4/3. R times r squared is r cubed. So 4/3 pi r cubed for the volume.